Today in Year 9 Mathematics, we're going to talk about similarities of shapes. So similar shapes, as you can tell from the definition of the word similar, you're going to talk about shapes that are related. So they are not the same shape, not the same angles, not the same lengths, but they are heavily related. So the technical definition of a similar shape, so looking at a pair of shapes and seeing if they are similar, is to first determine if they are equiangular, so seeing if they have all the same angles that make up the shape, or seeing if all the side lengths have the same ratio. So looking at the examples here, first example, we have two rectangles where we have a width of 3 and a length of 2 for the first rectangle, and a width of 6 and a length of 4 for the second rectangle. Now, so what we're trying to prove here is that the second rectangle is just an enlargement of the first rectangle. So we have effectively the same shape, but the rectangle has either been condensed or enlarged. So what we do is we find a ratio of the sides. So let's say we're finding the ratio of the width here. So we have 6 over 3 divided to give us 2. We need to see that we have the same ratio as when we are dividing the length, where we have 4 divided by 2, and lo and behold, we have a ratio of 2. So what we've found here is that the width and the lengths have both been increased by the same factor. So what that tells us is that we have the same original shape, but the whole thing has just been enlarged by a factor of 2. So in this case, we've found that we have found an enlargement of factor 2, therefore they are similar shapes. So looking at the second example here, we can see that we have a height of 3 for this triangle, a height of 1 for this triangle, and we also have a base of 1, 2, 3, 4, 5, 6 approximately for this triangle, and a base of 2 for this triangle. In this case, we have seen that we've gone from a height of 3 to 1. So we have a factor of a third there, and for the second length of the base, we have 2 divided by 6, giving us a third. So you can see here we have a reduction of 1/3. And this shape is also similar. So third example here, we've got a square and a rectangle. Now you can see here we've got two lengths of 2, and this one we've got 3, 6, 8, and a length of 2. So if we find the ratios of those two sides, so that one side has had an enlargement of a factor 4 and the other has stayed the same. So that tells us that this shape is not similar. Okay. So we see that we can find the similarity of shapes by looking at a factor of enlargement or reduction. So this scale factor, if you take a ratio of the side lengths with the final number being in the top position of your fraction, also known as the numerator, and the initial length in the denominator position, you will find the scale factor. Okay, and if you have a value less than 1, then you have, so a fraction, you will find that you have a reduction in the overall size of your shape, and if this fraction is greater than 1, then you'll have an enlargement. So final example here, just zooming in. So just looking at these two shapes here, just going to highlight the fact that the angles inside these two, well, triangles in this case, are actually the exact same, but the side lengths in this case have actually doubled. So you can see that even when you have enlargement, the angles stay the same. So to be similar shapes, we call it being equiangular. I.e. all angles are equivalent. Cool. Okay, so whenever you have similar triangles, so just a reduction or an enlargement, the angles inside those shapes, being a triangle, rectangle, square, no matter what, they will all stay the same. So having a look at a more textbooky example, so just highlighting here that the apostrophes, just let you know that that is the post-enlargement or post-reduction form of the shape. So without the apostrophes tells you that that is the before shape, and that number should go on the bottom of our fraction for the scale factor, and the apostrophe case will go to the numerator of that fraction for the scale factor. So if we just have a look at part A for this example. So what we are going to do is look at the ratio between the lengths of the after and before. So if I'm having a look at the top length of this shape and looking at the scale factor, so 6 and 4, you see that I have a scale factor of 3 over 2. So in that case, larger than 1, that is going to be an enlargement. And similarly for B and C length, 3 over 2, we get 3 over 2 again, therefore that's an enlargement. And therefore we have similar shapes. Okay, so looking at these second sets of triangles, once again we're going to look at all three lengths here. So looking at the post enlargement, or in this case looks like enlargement first, on the top of our fraction, 4 divided by 2, we get a scale factor of 2. And we just have to double check all sides fit this scaling factor, just to check that our triangle, oh, that's not good, is a similar triangle. 10 over 4, 5 over 2. So you see here we've got 3 different scale factors. So in this case, the triangles are not similar. There you go. All right, so in this other example here, we're going to determine an unknown, given that the figures are similar. So if they are similar, then we know that the lengths, or the ratio of the lengths 5 over 3, must be the same as x over 4, where the second shape lengths are in the numerator position and the second shapes are in the denominator. So to rearrange this and find the x, all we need to do is times both sides by 4, and just writing the leftover on the left now, we see that we have 20 over 3 as our x. So 4 times 5 over 3 times the tops times the bottoms, we get 20 over 3, and that was in centimetres, 6.67 centimetres. Cool. Okay, so that's it for today's lesson on similar shapes, and see you next time.